So in chapter 7, definition of the Laplace transform, it was the first part. Now the second part, inverse transforms and transforms of derivatives. And also we studied how to find the inverse transforms, right? And how to use transforms of derivatives to solve differential equations, linear differential equations with constant coefficients. Okay, now we will do some brief introduction to operation properties. Number one is translation on the s-axis, and the second one is translation on the t-axis. Now we will talk about translation on the x-axis. Okay, so now each time, for example, when we are talking about the Laplace transform, if you are given any function, right, y is equal to f of t, and that is defined over this interval, right? And to find it is Laplace transform, that is, that said, is f of s. How we are evaluating this? We're just using the definition, like Laplace transform of f of t. Oh, it looks so weird. Let me rewrite this. So Laplace transform of f of t, right? That is equal to, I don't know, it draws this unwanted line all the time, every time. Here we have f of t. And to calculate this, we have to use the definition, right? 0 to positive infinity, e to the power s of t times f of t dt. All right. But using this definition every time to evaluate the Laplace transform of a given function is not always easy, right? For example, if you consider this function, let's say if our f of t is, let's say, e to the power t, for example, t squared times cosine of, let's say, 5t. Okay, for example, or another function, f of t is equal to e to the power 3t times sine of 3, or let's say 4t. Okay, using the definition, can we actually find the Laplace transforms of these functions? We can, but it is a tedious job, right? It's a long procedure. Every time you need to evaluate the improper integral, and using the integration by parts, the technique even takes a lot of time. Okay, now to save this time, we are actually now going to get introduced with this formula. That is a theorem. This theorem actually makes some of our work much easier and short. It says that if you are taking the Laplace transform of first, if I multiply by e to the power at f of t, what is it? It's just simply equal to f of s minus a. Here, where Laplace transform of this f is equal to f of s. Okay, but why is it so? And proof is very simple. Here, that we can prove it. All right, let's say proof of the theorem. Again, using the definition, what is the Laplace transform of this e to the power at times f of t? Okay, and theorem means a kind of shortcut to evaluate this. Maybe this kind of functions appear very frequently in the future. So it's saying that every time you don't have to go through this procedure. You don't have to evaluate the Laplace transform of this kind of functions using the definition. If you know the Laplace transform of this f of t, just after finding this, that's f of s, instead of s, just substitute here s minus a. That's a shortcut. Why is it so? If you evaluate this, it's a proof of this theorem. It is from 0 to positive infinity. Here we have e to the power st, right? And here our function. What we have here? Here we have e to the power at times f of t and dt. Okay, I really don't like this line. I still couldn't understand why it's drawing like this. Anyway, equals e to the power minus st, e to the power at. So I can simplify this because bases are the same. E to the power minus, right? T is a common factor. Since they are multiplied, we should add their exponents. So here we have s minus a t times, here we have f of t dt. right? So actually it is exactly the same with the definition, right? The only thing is instead of S, here we have S minus A. Then what should I write here? If I have S here, I need to write capital S, right? But here if I have S minus A, whatever it is, I need to write here. So here we have S minus A, so I need to write here S minus A, right? In other words, what does it mean? This means that if I can evaluate the Laplace transform of this F, right? This F, that is capital F, that means that is just capital F of S, where I have to change this S into S minus A, okay? As a common shortcut. Now this is our first case. And that is actually, what is the translation about the x-axis? This S minus A, what does it mean? Here, let's say this one is S, this one is F. If the graph of this F is something like this, okay, and let's say this value is A is positive, right? S minus A means if A is positive, shifting the graph A units to the right. That means it started from here, it is something like this, right? So that is the graph of F of S. And how about this one? That is a graph of S minus A. Yeah, because we know that just adding constant to the x, right? It will just shift the function either to the right or to the left. If you're subtracting positive number from this independent variable, that means that the same graph is exactly the same copy of each. We are just shifting the graph A units to the right, right? If we add this, that means that A units to the left. And that's why we are saying that that is translation on the S axis. Okay. Example, let me just see these two examples and finish our class, all right? And we will continue next week. So two examples here. A, using the first translation theorem, evaluates the first thing. So that is Laplace transform of e to the power 5t times t cubed, right? And that is equal to, here we have f of t is equal to t cubed, right? So if I evaluate Laplace transform of t cubed, we have already evaluated this. What is it? It is equal to 3 factorial, right? N factorial over s to the power n plus 1. That's equal to 4. So that thing is equal to capital F of S. Using the theorem, what is it? This one is our f, e to the power at. That thing is capital F of s, but this value should be changed to s minus 5, because here we have a is 5, s minus 5, right? What is capital F? S is equal to this thing. That's equal to 3 factorial is equal to 6. So I have here 6 over s to the power 4, but s should be replaced by s minus 5, which is equal to 6 over s minus 5 to the power 6. Okay. How about question B? A similar thing here. This thing is, let's say, f of t, right? And this function is multiplied some exponential function e to the power 2t. Okay. So Laplace transform of f of t. Which is equal to Laplace transform of, what is f of t? It is cosine of 4t, which is equal to, we know how to evaluate this, that is s over s squared plus k squared. K is 4, here we have 16, right? Now if I evaluate Laplace transform of e to the power minus 2t times cosine of 4t, right? That is equal to, that thing is f of s. So here we have f of s, but I need to replace this s with s minus a. S minus minus 2, that is s plus 2, which is equal to our s, f of s is this, right? So now instead of s, I need to write this s plus 2. So it will be here, instead of, okay. Here S, here we have S plus 2. Here we have S, so here we have S plus 2 squared plus 16. Okay, that's all about what is that translation about the S-axis. Now we will do more examples, related to this. Maybe I will make some video and share with you guys. For today, that much is enough, all right? And I think everything is clear. So see you soon, maybe next Wednesday or next Monday. So what time you are available and when you want to do your presentation, let me know as soon as possible. So I'll make a schedule and share with you. Okay? Thank you very much. Bye-bye. Enjoy your lunch. See you next week.
Goodbye, sir. Have a nice day.
Yeah, thank you very much. Thank you. Bye-bye.